Welcome back to the second section of Chapter 5, DC voltage. In the previous chapter, we talked about the generalities, we talked about electric appliance symbols, we talked about types of circuits, series and parallel, and mixed as well. Now today, in this session, we're going to continue in another part, which is the electric current and voltage. So we'll define these terms and we'll talk about them in more details. Probably you have seen them or talked about them in previous classes, but now we're going to talk about more details concerning them. Where do we stand from the chapter now? We have covered the first three parts: conductors, schematic, and types of circuits. Today we're going to talk about electric current, definition, units, and how to measure and measurement. Also we're going to cover voltage, definition, unit, and measurements. Then, in the following section, we might talk about the laws of connection as for voltage and current as well. Let's roll. The electric current. We should always, and you will notice that I always do this, anytime we introduce a new term, I call it a new vocab, I define it. Yes, we should all agree on the same term. يعني بأول أي فكرة لازم يكون في definition لحتى لي أنا شو عم بقول وأنت شو عم تقول وهي شو عم تقول، نكون كلنا عم نحكي نفس اللغة ونفس المعنى. Okay, so vocabulary and definitions are very important at the beginning of any new item. The flow of charge in a circuit per unit of time is defined as electric current. So when we have charge, we said that electricity is all about the charge and the motion of the charge as well. Whenever we have a charge and that charge is moving, I can think about electric current or electric current intensity, which is the amount of that flow. So the flow of charge in a circuit is defined as electric current. Since we have two types of charge, positive and negative, so we have to be more specific. When we talk about electric current, we talk about the flow of charge, the positive charge, the flow of positive charge. If the charge in the circuit is negative, such as electrons, we take the current as the flow opposite or as the direction opposite to the flow of electrons. Okay? It's not that hard. We always consider the flow of the positive charge as the current. If the flow is that of negative charge, we take the direction of flow opposite to them. Okay? The symbol of electric current is letter I, and its unit is the ampere. The ampere symbolized by capital A. Now, what else? DC current. Our chapter is DC voltage, if you remember. DC current means constant current. We always use DC as standing for direct current. Now you notice when you say DC current, it's as if one is saying direct current current. It's not like that. It's a sort of a convention that when we say DC, it means constant. So when you say DC current, it simply goes to direct or to constant current. Okay? Now, DC current is a type of electric flow with constant value and the same direction of flow always. So that's very important to keep in mind. The flow of charge that we talked about is always in the same sense. Now, one more thing concerning language, okay? If you are a person who is picky concerning language, when we say electric current, it is the flow. So usually we do not say electric current flowing, we just say electric current present or found. Nevertheless, and I use that, it's fine, it's not the end of the world, okay? You can use electric current flowing, it's fine, okay? Now, okay, keep in mind a very important thing concerning electric current. In a closed circuit, the current flows throughout the whole loop simultaneously and as one unit, okay? So in an electric circuit, electric current always flows in the same direction and all together. We do not have partially flowing and partially stopping. If you take a look here, okay, here is a chain of a bike. It's not very clear. I think its quality is a bit low, okay? So this chain, the chain of the bike, flows all together. If it stops at a point, the whole chain stops. Always think of electricity like that. We do not have electricity flowing in a section and stopping somewhere else. Or for example, electricity moving to reach a point and stop there. It doesn't happen, okay? So, always keep this analogy, always compare these two ideas. This is the chain, this is the bike in a better definition now. So if we block the chain at a certain point, the whole chain stops rotating. It doesn't move anymore. The same thing happens with electricity. If I block, for example, by a switch or by anything, if I block the flow of electricity, the whole circuit stops electric flow. Okay? It's not that electrons or electricity is going to flow in a direction and stop here. No. One more thing you can notice in this figure, we have dots showing electrons and the red arrow showing the conventional direction of current. We will talk about that in more details since we're talking about electric current now. Yes, however, we should always distinguish between electrons and current. Why? We said that electric current, by definition, is the flow of electric charge. And by convention, we agree on the positive charge direction is the direction of current. If the circuit doesn't have positive charge, it has negative charge, so we take the direction opposite to that negative charge. By this, all of us, all people around the world, speak the same language concerning electricity. So that's why you notice that electrons or these blue dots are moving in a direction while the red arrow is showing or pointing in the opposite. Okay, moving on now. Let's see this, what we talked about in a certain animation. So we agreed on the generator drives electricity. So the generator, as you can read here, drives electrons in a circuit. Okay, it drives electrons from its negative pole, and we'll see that, pushes electrons to the circuit, they flow and come back to the positive pole of the generator or the battery. Okay, by convention, we talked about this, now we see it written. The current direction is chosen opposite to the flow of electrons. So, if you want to memorize something, in a closed circuit, electric current is directed from the positive pole of the generator towards the negative pole of the generator as well through the circuit, not through the generator. Pay good attention to that. You might drop it right now, it's okay, but the true and the accurate description is to mention it is through the circuit. So, electric current is by convention from the positive to the negative. Electrons flow from the negative to the positive. This is by experience, not only by convention. Okay, over here, let me move aside to see it. This is the generator connected to a circuit. Now here we have wires. I used here an application called the FET application. Let me just pause it. Sorry for that. Okay. So in this application, they show you electrons in the wires. So imagine that we have electrons, these blue dots here. They are the electrons in the circuit. Notice the whole circuit contains electrons because it's made up of conductors. That's number one. Second, we have a lamp. Now the lamp is giving light because when I accidentally clicked this, the switch was closed. So there was a switch here, which was open at the beginning, a generator, a battery, and connecting wires. Now, notice, as I play this, notice the direction of flow of the blue points, which are the electrons. Notice this. Electrons are flowing like this, right? So the flow of electrons is counterclockwise, opposite to the arms of the clock, right? Nevertheless, in this situation, this is the positive, this is the negative. Electrons go out of the negative side. When the battery gives a negative or an electron to this side, it pushes it away. This electron pushes another, the electron pushes another, etc. through the circuit until it reaches here. Over here, the battery or the generator or the dry cell takes an electron from the circuit. So you notice that almost the battery didn't lose anything. It simply took an electron from one side and pushed the electron on the other side. The battery is a driver of the electrons, okay? It supplies the energy for this electron to flow and in the circuit. Now, if you continue the motion of these electrons in the battery, they moved like this, from plus to minus in the battery. Okay, that's why it's always important to mention that electrons flow in a certain sense, or current in the circuit is directed from positive to negative through the circuit, not through the battery. So electrons flow from minus to plus and continue plus to minus inside the battery, while current, okay, so this is the positive, this is the negative. Electrons are moving like this, while electric current is like this. So keep that in mind. Electric current is always opposite to the flow of electrons. Electric current flows from positive to the negative, but through the lamp or through the circuit. Now, if I continue running this, you notice electrons flowing inside the battery from plus to minus, a whole loop. When we open the circuit, the whole circuit stopped. It doesn't move like gradually, as one unit. Always remember the chain of the bike. Continuing this. Okay, then when we close it, the whole circuit moved. So two main ideas, or three main ideas we get from this animation here. First, a circuit is made up of conductors which are rich in electrons, in free electrons. Electrons flow from the negative to the positive pole of the battery in the circuit. Electric current flows from positive to the negative in the circuit as well. Third and very important one is that the whole current or the whole circuit is traversed by the current as one unit. Current flows as one unit. It doesn't flow gradually or move and slow down. No. It's either a current is found in the whole circuit or not. Okay? Now, moving on. The electric current now as a unit. We said before that the unit of electric current is the ampere. Nevertheless, we have some other units. The basic ones that I've chosen here are the kiloampere, which might be used usually in industry. Okay? 1 kiloampere is 1000 amperes. Now we have the milliampere, which is a smaller unit. 1 milliampere is 0.001 ampere, or 1 over 1,000 of an ampere. In our bodies, we have electric current. In any appliance at your house, we have electric current. In your cell phones, there is an electric current. Now, other units we have the megaampere, which is of minor importance, okay? And we have, so this is not very important. And we have the microampere. This is just for information. Please don't memorize it. It's the microampere, okay? It is a very small unit. A microampere is the current flowing in your bodies. When your nervous system functions, it uses microamperes level. Milliamperes is found in electrical appliance, for example, in a computer or in a TV or in cell phones. Now, as an example, an AC in your house consumes electricity. It functions with a certain voltage. This is something else. And it consumes around 5 amperes. A 9000 BTU ampere. You know, ACs, a 9000 BTU AC. Air conditioners come with at different levels. If it's a 9000, it needs around from 4 to 6 amperes in general. A calculator, the calculator that you use, functions using 2 milliamperes approximately. Our bodies contain current of around 0.2 microamperes. So yes, we have current almost everywhere around us. Let's take this simple application in which we need to convert these units into ampere. How to convert 2500 milliampere into amperes? So 2500 milliampere. I know that milliampere is a divide by 1000, so I can simply do 2500 and divide by 1000, okay, ampere, which becomes directly 2.5 amperes. Okay? Or you can simply do it mentally when it comes to easy stuff, 0.75 kiloampere. What I like to do usually is take the prefix K and replace it by 1000. So this becomes 0.75. Allow me to use 10 to power 3 now, ampere. I think you are familiar with powers of 10. You know, you move the decimal point 3 steps forward to give 750 amperes. Double checking, yes, all is good. Okay, so this is a simple application about conversion of units. Now, measurement of an electric current. How do we measure electric current? What is the device that we use to measure electric current? Basically, in order to measure an electric current, we use a device called an ammeter. The ammeter is simply an instrument which it can be, by the way, analog with a needle or digital like this device here. Okay? Over here I've chosen a device which is a multimeter. A multimeter has many functions. Nowadays, instead of buying an ammeter, we can get a multimeter which has all these functions. Okay? So the ammeter should be connected in a certain way in the circuit. It is always connected in series with the studied device. In series. So if you have a full circuit combined together, you have to cut or remove a wire and add the ammeter across it. You will see it here. I have this electric circuit over here, a generator, connecting wires and a load. Notice when we connected the ammeter, what happened? Check this. We remove this wire and add the ammeter. So electricity flowing here. Now I can say that electric current flows like this. Electric current I flowing. And it's better that we use electric current found, but it's fine. Okay? Again here and here. It continues its direction into the ammeter. The ammeter reads the value crossing it, which is the current in the circuit. Okay? Another note we need to keep about ammeters is that the ammeter has a very negligible resistance to current flow. Electric resistance is simply the action against the flow of charge. Okay? The COM terminal, whenever you have an ammeter, the ammeter has an entry and a negative pole. The entry is referred to as letter A, and the negative pole is referred to as the COM. So the COM terminal should always be connected to the negative of the generator. So if I go back to this circuit here, the ammeter connected has this side as COM. Some people refer to this as letter A, or indicating the positive pole of the ammeter. Now, the proper connection of the ammeter is like this. But if you reverse the connection, it's not the end of the world. All that you're going to have is negative reading in the ammeter. Okay? So if you just reverse the connections, it remains correct, but it will display negative reading. The symbol for an ammeter, as you saw there, we draw A and place COM and plus. This plus can be removed and replaced by letter A. I prefer to use this usually, by the way, because having a lot of plus signs in the circuit might be a bit confusing, especially if you have many ammeters. Okay, now we can also use, as we said, another device is the multimeter, which is an instrument that can do many functions. However, when you use the multimeter, you need to add one more point concerning description, which is the multimeter has a dial. This dial has many options. It has the V as voltage, it has ohm as something else later. We choose this, the part showing letter A. By the way, if you look closely, you will find A, above it lines, dashes, and one line like this. This symbol is symbol of DC. Okay, so this is the symbol of DC. Let me just fix this. Okay, now. Okay, so if you are using a multimeter, just add this notion that you're going to use the ammeter under the mode of the multimeter under the mode of an ammeter, and we need to turn our dial towards A, wherever letter A is found. And we should also use these entries, A and COM, because we have A, COM, V, we have to use A and COM. Okay. If you want to use an ammeter, what are the cautions or precautions that you have to take into consideration? We said that it's connected in series. That's something easy. First, we choose a range. What is a range? A range is simply a value which is the maximum reading of the ammeter in this case. Over here, I have a multimeter having V, notice V with a dash, DC. This is something we'll study later. V with a wave, which is not required right now. What I need to worry about is the A. Where is the A? Here it is. And we have this as well. So A is the ammeter functioning and mode. We have values as 200 micro. You know micro is 1 over a million. We have the 2000 micro, we have 20 milli, 200 milli, and we have one key which is 10 ampere. I always like to use this. 10 ampere can measure everything up to 10 ampere. And by the way, 10 ampere is quite a large value. 1 ampere is large value. Off the record, humans are electrocuted with a current of 30 or 40 milliamperes. يعني نحن بس نتكهرب، الكهرباء ما بتكون 1 امبير. انجا بتكون 100 ملي امبير، 100 ملي امبير خطره كثير. So yes, when we deal with electric current, don't expect to have huge values. Okay? So we choose here the 10 ampere. So this device is able to read now up to 10 amperes. Okay? So we choose a range. What I advise you to do is always choose the highest range possible because it reads everything. But if you choose a high range, for example 10 ampere, and you're measuring a current of 0.1 ampere, the accuracy of reading is going to be very low. So if you are reading 0.1 ampere or 100 milliampere, it's better to choose a value closer to the 100 milliampere. So we choose the highest range. Start decreasing the range until you reach the most precise value. But it should be a value, not a disappearing value. For example, if I'm reading 2 amperes, when I drop from here to 200 milliampere, which is less than, it won't function anymore. If the range chosen is less than the measured value, you are measuring 5, and you choose, let's say, 200 milliampere, the ammeter simply registers and shows you number 1 to the left-hand side. You'll just see 1 here. Notice? Now, if the COM is connected to the positive pole or closer to the positive pole of the generator, the ammeter still gives you a value, but it's going to become negative. So these are 2 ideas you have to keep in mind. If you choose a range less than what you're measuring, it displays 1 to the left, that's an indication, please increase the range. And if the reading is negative, that's an indication that the current is flowing in or is moving in the opposite sense. You have to reverse the connections. It's okay, if the reading is negative, it's fine. As for me, I keep it as it is. And all I do is when I write the value, I just write it 2.5, not minus 2.05 as shown here, for example. Okay? That's it concerning the range. Pay attention. We start by the highest range and we decrease. The best range, let me add it here, best range, the best range is the smallest one, the smallest range, continue here, greater than the measured current, or the measured current, yes. Okay? Excuse me for the mess, but I found this an important idea. So to choose a convenient range, choose a range above the value you're measuring or you are expecting, and the first one above. So if you have, let's say, 10, 2, 5, all of these are above the measured value, you choose 2, the least one. Okay. Now, we finished with the current, we move to the voltage. Now, when we talk about electricity, basically in electricity we have 2 important things, 2 important elements. These are the current, the amount of charge flowing, and we have the voltage, the energy of the charge which is flowing. In fact, the definition of voltage is the electric energy supplied or consumed by the generator or the device per unit charge. So if I have a lot of charge or a lot of electrons moving, electrons have charge. Charge has a unit. 1 unit of charge, which is the coulomb, which is not covered now, 1 unit of charge takes or requires an amount of energy to move. I need some energy to push it, to push this 1 coulomb. This energy is called voltage. So, when you need to drive electricity in the circuit, you need to consider 2 things. First, how much electricity are you going to move? That is the current. And how much energy is required to move them? That is voltage. So anytime we study electricity, we must always consider these 2 things, voltage and current. And that's why we are giving them a lot of time. The symbol of voltage is letter U capital or V. I would use it U in general, but both are accepted. And its unit in SI is the volt, symbol V, capital V as well. Again, in DC voltage, we say DC voltage, as the title, by the way. DC voltage, if you translate it word by word, direct current voltage, which doesn't make sense a lot. But as we said, it's a sort of agreement that DC means constant. DC voltage stands for constant voltage, which is constant in value and keeping the same polarity. Okay. Voltage of a battery, which is very important here. A battery is characterized by its voltage. We assume that the voltage of the battery is fixed. It has one value. It maintains across its terminals a constant voltage that is referred to as voltage of the battery. Now, when we buy a battery, after some time, this battery is gonna dry up. When a battery dries up, it has no more voltage between quotations. Now, in our study, we consider that the voltage of the battery, let's say I bought a 1.5 volt battery, that voltage remains 1.5 always. So as if the battery functions with 1.5 volts or doesn't function. In reality, that's not true. In reality, 1.5 volt might decrease with time. Yes, but we do not consider that when we study. So I will not mention this and I will not talk about it. What we study here is the theoretical study. We have a 9 volt battery. You all are familiar with this battery, right? We have the accumulator. This is a car battery delivering 12 volts. It's always constant. If you go to an appliance also needs voltage. Now, off the record again, the functioning of an appliance depends on both the current and the voltage. But for the time being and for grade 9, we consider that the functioning of an appliance depends on its voltage. And we call that rated voltage. We define rated voltage as the voltage needed by a device to function normally. I've taken here two pictures, one of a router, since we are relying on routers a lot nowadays, right? And one of a laptop. On a router, we have 9 volt. So 9 volt line 0.6 ampere, meaning this router functions under a voltage of 9 volts properly, DC voltage, and 0.6 ampere. Now, I will not talk about this. Let's think about it that this router needs 0.6 ampere. But I will not talk about it. I'll talk about another example, which is a laptop. This laptop needs 19 volts. It's 19.2, yes, it's 19. 19 volts to function properly. This is the rated voltage. You just say rated voltage of router, rated voltage of laptop. Other units of voltage, since we have the volt as the basic, we have some others. We have the kilovolt, 1000 volt, just like we said about the ampere. We have the millivolt, which is 10 minus 3. Now the megavolt is found 10 to the power 6 volts. It is found a lot, especially when we go to high tension wires. خطوط التوتر. You can think about that, okay? They are called high tension wires, high voltage wires. عندهم voltage كتير عالي, okay? An example, if you want to convert these, 1500 millivolt converted to volts, as we said before. Take the milli, which is divided by 1000, and write 1500 divided by 1000 to become 1.5 ampere. Same thing here, but kilo, so it is 2500. Notice here, I allowed myself to do it mentally, and I told you this. If you find problems with that, don't worry. All you have to do is just show it like this. Let me move it. 2.5 instead of the kilo is 1000. Okay? So this is 2500. And the last one is in megavolt. A mega is 0.06. Sorry, it's 10 to the power 6. Okay? Times 10 to the power 6 volt. So now I move the decimal point forward 6 times. 2 steps will cancel the 0.05. So I get 5. Then I have 4 other zeros. So this is a 50,000 volt. Okay? This is concerning the unit of voltage. Now, measurement of voltage. Again, we need a device to measure the voltage. This time the device is called a voltmeter. The voltmeter is connected in parallel, not like the ammeter. It's connected in parallel across the device. Again, if you are using a multimeter, you use the outputs COM and V, not A. I told you that a multimeter has 3 outputs. Connections in the circuit are, okay, let's see them in the circuit, then we read these. Again, the same circuit that we talked about in the previous part. Okay, so far this is what we have seen before, right? Now adding the voltmeter, notice the voltmeter I can add here like a connection wire. The voltmeter is connected across the load. And again, the voltmeter has a COM, so I'll choose a convenient color. The COM is always adjusted and placed closer to the negative side. As we talked about the ammeter, we talk about the voltmeter here. Again, the voltmeter has a very high resistance now. Why does it have a very high resistance to current? Because as current flows here, current is flowing, you know, current flows from positive to negative, right? When current flows, it reaches this splitting point, it reaches a splitting point. But since here we have high resistance, it will resist the flow of current, so current continues through the load. So the voltmeter doesn't affect the circuit. The COM terminal is connected closer to the negative, and we talked about that. As for the symbol, we use COM and V. Now, okay, over here I added the ammeter, by the way. So if you want to measure voltage and current, you can simply go to voltage and ammeter. Okay? Now, using the voltmeter, I will go over this quickly because it's almost the same as the ammeter, but in volts. Not only that, voltmeters have different ranges, more vivid, more rich with values, more than the current. You notice that the DC voltage here in this multimeter has 1,000, 220, 2,000 millivolt or 2 volts and 200 millivolt. You can choose any range that you want. We always start by the highest range and we start moving down. Once we reach a range which gives number 1 on the left, that means, yes, your range is less than the measured voltage, so increase it. And if it happens and the reading is negative, that means I connected the voltmeter in the opposite way. Either unplug and connect in the opposite way, or simply keep it as it is. I would do that, okay? Unless the question is, connect the voltmeter to give a positive reading. In problem solving, you know what to do. Okay, over here we have an application. Now, I will not solve it. Yes, we'll have like a specialized session to solve applications. I want you to try to solve it on your own. You can find it, by the way, in the section where you can find quizzes and exercises. This is an application found within the exercises. So we have a circuit composed of a battery and a lamp, and we have a multimeter here. The multimeter is needed to measure the voltage. The lamp functions normally. Why? The multimeter is used to measure the voltage across the lamp and to give a positive reading, show the connection, and then the ranges are 2, 10, 20, and 200. Which range is the most convenient? Simple, it's not hard. Take a look at it, try to solve it, and later on you can check the solution. Okay? As for now, thank you for your time. We have finished this section. It was a long section, as I told you. We have finished everything about electric current and voltage. Go over this again, pause, watch over and over. If there is any point that you don't understand or you don't get, don't hesitate to ask us in the comments. Have a nice day and thank you for your time.